An ungrounded electrical system is a system where one or more conductors, or phases, are not connected to electrical ground. In a typical three-phase system, the A, B, and C phases are all connected to a ground wire, which is then connected to the earth. However, in an ungrounded system, one or more of these phases is not connected to ground. Ungrounded systems were sometimes used in the past for a few reasons. Firstly, reduced risk of ground faults. In a grounded system, a fault, or short circuit, in one phase can cause a large amount of current to flow through the ground wire, potentially causing damage to equipment and electrical components. In an ungrounded system, a fault in one phase will not allow current to flow through the ground, reducing the risk of damage. Secondly, improved power quality. Ground faults can cause voltage sags and other power quality issues. By eliminating ground faults, ungrounded systems can improve the overall stability and reliability of the electrical system. While ungrounded systems can offer some advantages, there are also significant safety concerns associated with them. Firstly, increased risk of electrical shock. In an ungrounded system, a fault in one phase can cause the voltage on the other phases to rise to dangerously high levels. This can increase the risk of electrical shock for anyone who comes into contact with the electrical system. Secondly, difficulty detecting faults. In grounded systems, faults are typically detected by the tripping of circuit breakers or fuses. However, in ungrounded systems, a fault in one phase may not cause any immediate problems, making it difficult to detect and correct. In most jurisdictions, ungrounded electrical systems are required to be posted with warning signs to alert personnel to the potential hazards. The specific requirements for posting may vary, but typically the signs will indicate firstly that the system is ungrounded. Secondly, the potential hazards associated with ungrounded systems. And thirdly, instructions on how to safely work on or around the system. Resources such as National Electrical Code Section 250.12, IEEE Standard 141 grounding of industrial and commercial power systems, and electrical equipment grounding general considerations can be referenced. Ungrounded electrical systems are no longer common in new installations. While they may offer some advantages, the safety concerns associated with them outweigh the benefits. If you encounter an ungrounded system, it is important to be aware of the potential hazards and to follow the necessary safety precautions. When working with an ungrounded electrical system, it is crucial to understand its characteristics and potential risks. Because one of the phases is not connected to ground, the system behaves differently than a grounded system. A ground fault on one phase doesn't create a direct, low-impedance path for fault current to flow back to the source. This can prevent overcurrent protection devices, like circuit breakers, from immediately tripping. This is both a benefit and a hazard. It prevents nuisance tripping in some situations, but it also means that a ground fault can persist undetected. The first ground fault in an ungrounded system doesn't usually cause an immediate outage. However, it raises the voltage of the other phases with respect to ground. If a second ground fault occurs on a different phase, a high fault current can flow between the two faults, potentially causing damage. This is why ungrounded systems are sometimes called floating systems. Their voltage with respect to ground can drift or float, especially when unbalanced loads or insulation faults are present. To address the safety concerns associated with ungrounded systems, several precautions are necessary. Regular insulation testing is vital. This involves using a megameter to measure the insulation resistance of the conductors. Low insulation resistance indicates a potential ground fault. Periodic testing can help identify insulation degradation before it leads to a fault. Ground fault detectors can be installed. These devices monitor the system for ground faults and provide an alarm or trip the system when a fault is detected. There are various types of ground fault detectors, including ground fault relays and ground fault indicators. Isolation transformers can be used. These transformers isolate the ungrounded system from the grounded source, providing an additional layer of protection. Personnel working on or near ungrounded systems should be trained in the specific hazards and safety procedures. They should use appropriate personal protective equipment, such as insulated gloves and tools. Warning signs should be prominently displayed to alert personnel to the presence of an ungrounded system. These signs should clearly state that the system is ungrounded and that there is a risk of electrical shock. Proper grounding of equipment is still essential. While the system itself is ungrounded, equipment enclosures and other metal parts should be properly grounded to provide a path for fault current in case of an insulation failure. This helps to minimize the risk of electrical shock. When troubleshooting an ungrounded system, it's important to use a high impedance voltmeter. A standard low impedance voltmeter can draw excessive current and potentially cause a false reading. A high impedance voltmeter minimizes the current draw and provides a more accurate reading. When measuring voltage to ground, remember that the voltage on each phase will be different due to the floating nature of the system. A healthy ungrounded system will typically show some voltage to ground on each phase, but the voltages should be relatively balanced. A significant difference in voltage between phases indicates a potential ground fault. Capacitive coupling between the conductors and ground can also affect voltage readings. This is especially true in long cable runs. The capacitance can create a path for current to flow to ground, even when there is no direct fault. This can make it difficult to pinpoint the exact location of a fault. Ungrounded systems are more susceptible to transient overvoltages caused by lightning strikes or switching surges. These overvoltages can damage equipment and cause insulation failure. Surge protection devices should be installed to protect against transient overvoltages. Regularly inspect the system for signs of damage, such as cracked insulation, loose connections, and corroded components. Address any issues promptly to prevent them from escalating into more serious problems. Keep accurate records of all maintenance, testing, and repairs performed on the system. This helps to track the system's performance and identify any recurring issues. When modifying or expanding an ungrounded system, ensure that the new components are compatible with the existing system. Consider the impact of the modifications on the system's overall performance and safety. Because ungrounded systems can be more challenging to troubleshoot than grounded systems, it's often best to consult with a qualified electrician or electrical engineer who has experience with these systems. They can provide expert guidance and assistance in identifying and resolving any issues. When working on an ungrounded system, always de-energize the circuit before starting any work. Use a voltage tester to verify that the circuit is de-energized. Lockout-tagout procedures should be followed to prevent accidental re-energization of the circuit. If you're not comfortable working on an ungrounded system, don't attempt to do so. Seek assistance from a qualified professional. When a ground fault occurs in an ungrounded system, it's important to locate and clear the fault as quickly as possible. This helps to prevent a second ground fault from occurring, which could lead to a more serious problem. There are several methods for locating ground faults in ungrounded systems. One method involves using a ground fault tracer. This device injects a signal into the system and then uses a probe to trace the signal back to the location of the fault. Another method involves using a process of elimination. This involves disconnecting sections of the system until the fault is isolated. Once the fault has been located, it should be repaired or replaced as soon as possible. After the repair has been completed, the system should be tested to ensure that the fault has been cleared. It's also important to investigate the cause of the fault to prevent it from recurring. This may involve inspecting the wiring, equipment, and environment for any potential problems. Ungrounded systems are not inherently unsafe, but they do require a higher level of knowledge and care to operate safely. By following the proper safety precautions and procedures, you can minimize the risk of electrical shock and other hazards. It's also important to stay up to date on the latest codes and standards related to ungrounded systems. The National Electrical Code and other industry standards provide valuable guidance on the safe installation, operation, and maintenance of these systems. Remember that electrical work can be dangerous, and it's always best to err on the side of caution. If you're not sure about something, ask a qualified professional for help. Proper grounding and bonding are also crucial in an ungrounded system, even though the system itself is not grounded in the traditional sense. Equipment grounding conductors should be properly sized and installed to provide a low impedance path for fault current to flow back to the source in the event of an insulation failure. Bonding jumpers should be used to connect all metal parts of the system together to ensure that they are at the same potential. This helps to minimize the risk of electrical shock. When selecting equipment for use in an ungrounded system, it's important to choose equipment that is specifically designed for use in these systems. Some equipment may not be compatible with ungrounded systems and could be damaged or create a safety hazard. Regularly inspect electrical panels and enclosures for signs of corrosion, water damage, or other problems. Address any issues promptly to prevent them from escalating into more serious problems. Ensure that all electrical connections are tight and secure. Loose connections can create heat and resistance, which can lead to equipment failure and safety hazards. Keep electrical equipment clean and free of dust, dirt, and other contaminants. These contaminants can reduce the insulation resistance of the equipment and increase the risk of electrical shock. When working on or near electrical equipment, always be aware of your surroundings. Avoid touching any metal parts of the equipment unless you are sure that they are properly grounded. Keep a safe distance from energized equipment to avoid accidental contact. If you see any signs of smoke, fire, or unusual noises coming from electrical equipment, immediately de-energize the circuit and call for help. Do not attempt to extinguish an electrical fire with water. Use a fire extinguisher that is specifically designed for electrical fires. Remember that electricity can be deadly, and it's important to take all necessary precautions to protect yourself and others from electrical hazards. Stay informed, stay alert, and stay safe. Ungrounded electrical systems, while less common today, present unique challenges and safety considerations. Understanding their operation, potential hazards, and proper maintenance practices is crucial for anyone working with or around these systems. Remember to prioritize safety, follow industry best practices, and consult with qualified professionals when necessary. The key takeaways regarding ungrounded electrical systems include firstly the fact that they lack a direct connection to ground on one or more phases. Secondly, the advantages include reduced ground fault current and improved power quality in some scenarios. Thirdly, the disadvantages include increased risk of electrical shock and difficulty in detecting faults. Fourthly, posting requirements mandate warning signs to alert personnel of the system's ungrounded nature and potential hazards. Fifthly, regular insulation testing, ground fault detection, and proper equipment grounding are essential safety measures. Sixthly, qualified personnel should be trained and equipped to work safely on ungrounded systems. Seventhly, NEC Section 250.12 and IEEE Standard 141 provide valuable guidance on grounding and safety practices. Eighthly, older buildings may still have ungrounded systems, requiring vigilance and adherence to safety protocols. And ninthly, consulting with experienced electricians or engineers is recommended for troubleshooting and maintenance. Finally, staying informed about the latest codes, standards, and best practices is crucial for ensuring the safe operation of ungrounded electrical systems. By understanding these key aspects and implementing appropriate safety measures, one can effectively manage the risks associated with ungrounded electrical systems and maintain a safe working environment. Always remember that electricity demands respect and a thorough understanding of its principles to prevent accidents and ensure the well-being of all personnel.